Before we put millions of components on a single microchip, controlling electricity meant heating metal plates inside fragile glass vacuum tubes. These bulky devices essentially boiled off electrons to get them to move. Today, we use something far more elegant, the semiconductor diode. A diode is a microscopic one-way street for electricity, built by joining two specifically treated pieces of silicon to form what's called a p-n junction. When you connect a battery in the normal direction, a setup called forward bias, the voltage easily pushes charges across this junction. The gate swings wide open and current flows freely. That reliable, forward-flowing traffic allows our computers to process logic. But the true test of a diode's design, and where the physics get slightly dangerous, happens when we try to force electricity to flow backward. Let's look at what occurs when we reverse the circuit. By turning the battery around so its positive terminal connects to the N side and negative to the P side, we create reverse bias. The external push from the battery aligns perfectly with the internal barrier potential instead of fighting against it. Because these forces stack together, the central depletion zone rapidly expands outward, sweeping mobile charges away. The barrier height becomes the original voltage plus the applied voltage, creating a towering electrical wall that totally blocks the main supply of charge carriers. By simply flipping the battery's orientation, we harness the diode's own internal electric field to construct an impenetrable microscopic force field. The main electrical current is stopped cold. You would expect a barrier this thick to drop the current down to absolute zero, yet it doesn't. A tiny, almost imperceptible leak gets through. To find the leak, we have to look for what physicists call minority carriers. These are the rare, stray electrons wandering around the P side and the isolated holes trapped over on the N side. That towering electric force field is perfectly designed to block the majority of charges. But for these sparse, wandering minority particles, the direction of the field actually acts like a steep slide, instantly sweeping them across the junction. This specific movement of minority charges driven by the electric field is called drift current. Because there are so few of these particles to begin with, the resulting current is a microscopic trickle, usually measured in tiny fractions of an amp, called microamperes. The main gate is heavily bolted shut against the bulk of the electricity, but the extreme physics of that very same force field leaves a tiny back door permanently propped open for the minority. To understand how engineers account for this hidden microscopic behavior, we have to look at how it translates into measured data. This chart shows the voltage current, or VI, characteristics of a diode. We are looking specifically at the bottom left quadrant, where the horizontal axis tracks the reverse voltage and the vertical axis tracks that tiny reverse current in microamperes. As we start increasing the reverse voltage, pushing harder against the barrier, the line indicating current drops slightly and then goes completely flat. Increasing the battery voltage doesn't increase the flow of electricity. The current is strictly limited by the physical scarcity of minority carriers in the silicon. The battery can push as hard as it wants, but there just aren't enough particles available to carry more charge. Because the current maxes out at this incredibly low level, physicists formally call this flatlining phenomenon the reverse saturation current. This flatline is a tense, highly strained equilibrium. It is a permanent stalemate between the immense electrical pressure from the battery and the bare physical lack of available particles to do the work. So what happens if we ignore that stalemate? What happens if we keep cranking the reverse voltage higher and higher and higher? The electrical pressure across the depletion region begins to build to an extreme degree. The force field blocking the main current is pushed far beyond the limits it was manufactured to withstand. Eventually, the material hits a critical structural limit. In physics, this threshold is the breakdown voltage. On the VI chart, this invisible tripwire sits at the end of the flatline. The moment we cross the breakdown voltage, the force field shatters. Resistance collapses, allowing a sudden, violent, near-vertical surge of reverse current to tear through the circuit. The safety of the saturation limit is gone. The reverse current is no longer restricted by sparse minority carriers. The floodgates are completely open, and a massive volume of electrons rushes in. Without an external safety circuit to throttle this wild surge, the sheer volume of electricity generates immense friction. The resulting heat will literally melt the silicon junction in milliseconds. The p-n junction is an incredibly efficient master of directing microscopic traffic.
But if you push its invisible wall too far backward, it completely destroys itself.